Hello and welcome back. It is time now to talk about condensation polymerization. So let us refresh our memory a little bit about the polymerization that we've already encountered. Almost certainly last year you would have encountered this addition polymerization. This is the kind of polymerization that happens to alkenes. Remember those hydrocarbons that contain the double bond? Well, what if we break the double bond? Then there's a pair of electrons, well, one on each carbon now, that could go on to form a bond to another molecule. Now, as itself, ethene is the monomer for something that we would call polyethene or polythene. We can join them together, they simply add on to the end of the chain. But to break that carbon double bond in the first place requires high pressures, high temperatures, and quite often a catalyst. Now this addition polymerization isn't the only type of polymerization that we have, and now we're about to step into the next kind. So if it's not addition polymerization, then what is it? Well, we're going to talk about condensation polymerization. It is again the joining of monomers, but this time there is a specific detail. A small molecule is lost in the junction between the two monomers each time. Now normally, and the most obvious example is when water is lost, and that's why we get the name or use the name condensation. When water appears on your bathroom mirror, we would call it condensation. In this joining together of monomers, water is coming out of these larger molecules. So we're going to look at that in a little bit more detail. But even though water is the most obvious thing that could come out, it is possible to choose different monomers where a different chemical comes out. And the ones that we will also talk about in this is hydrogen chloride, HCl, but it's also possible for ammonia or hydrogen to condense out in this polymerization. The key thing is the condensation doesn't refer in this case to the production of water. The condensation talks about the production of a small molecule in the process of polymerization. And this is really important because condensation polymerization is the mechanism by which we form most plastics. Polyesters, polyamides, we're going to go into a lot of detail. And now these plastics produced are used in a variety of different ways, but there's going to be a focus, as you'll see, on synthetic fibres and clothing made from these polymers. The simplest kind of polymerization, for example, that which forms a polyester, is when we have one monomer repeating itself again and again and again. Now for this to be possible, we have to have atoms on the edges of that monomer compatible with joining on to the next one. And that, for this example, requires carboxylic acid on one end of your monomer and an alcohol group on the other. Glycolic acid, this thing here, it's as a substance, it's a treatment for acne. It's a substance that is very, very good at basically severing the bonds between skin cells that are alive and skin cells that have died. It's an exfoliant is what its present use. But believe it or not, because it has this property of having a carboxylic acid group on one side and an OH group on the other side, they can all hold hands and join up. So the OH group in the carboxylic acid can react with the hydrogen that is in the alcohol group of the neighbouring monomer. And so what you can see is that there's an OH and an H. Together that makes water. And so what happens is the water fits together and moves out of the chemical. The two remaining parts of each monomer, then they join back together around that oxygen bond. It means that there's an oxygen in the middle of the chain now, and we call that an ester link, remembering that we defined an ester to be a chemical that had an oxygen mid-chain. So look, we've joined together two monomers. We've expelled a water molecule, and we've now got something that has two carboxylic acid groups in. You can see that's why we would call it a dicarboxylic acid at this point, with an ester link in the middle. So what happens when we join together glycolic acid? Well, we're going to get this thing polyglycolic acid. Notice how we put the brackets around the monomer and then we wrote the word poly in front of it. How we display that? Well, I've got two different ways of displaying it. First of all, we draw brackets around the monomer. We have the bonds going off to other monomers drawn outside of the brackets with an N to represent how many repeating units of this monomer we have. Now, it is possible to draw the backbone of the structure as a horizontal line showing like a structural formula version. But we can also draw a skeletal formula where the hydrogens are not drawn and the carbons are represented by the vertexes of the structure. So what is polyglycolic acid? Well, it's no longer a treatment for acne. It actually produces a polymer, which is a fantastic biodegradable polymer, one that over the period of 6 or 7 weeks will slowly fall apart and revert back into monomers once more. Now that's because, in this case, if the monomers stuck together and expelled water to form the polymer, when it comes under attack by water, will split back up into its monomers. And what will happen is this material, absorbing water from your body, will break down. And so we use it for dissolvable stitches. The entire industry of producing this one polymer is worth between $0.5 and $1 billion every year, because this material is used in nearly all biodegradable stitches in every hospital in the world. How about lactic acid? We are all used to lactic acid in our muscles when we run faster than we can breathe. But did you know that also lactic acid can act as a monomer, that we can join multiple versions of these together and form polylactic acid? Well, polylactic acid forms a kind of plastic, a kind of waxy, beady sort of plastic. But the thing that's most unusual about this is because it, first of all, it can be made from cornstarch. We can harvest a crop that produces the raw ingredient to make this plastic. It means it is not derived from oil. It is a kind of plastic that sits completely separate to our fossil fuel industries. Alongside that, in the same way as the previous example, it will come under attack by water and slowly break down into its monomers once more. That whilst dry, it will have all of the properties of plastic. Once wet, it will break down into small biodegradable molecules. This means this is our best biodegradable plastic. And what we use this for is for making things like throwaway items, or single-use plastics like cutlery and things like that. The limitation is, of course, it comes under attack by water. As soon as it gets anywhere near water, it starts to biodegrade. And so it's not a suitable plastic for example, storing milk, because the milk, or the water in the milk, would attack the plastic and it would leak. It has to be only used in those situations where the plastic is kept dry. Polymers aren't always as simple as those that are made of a repeating single monomer. Sometimes you can have polymers made of combinations of different monomers. And all of these, this whole family, are called copolymers, where it's 2 or more different monomers. And we're only going to look at one type here, but just so that you're aware, there are different types. There are alternating copolymers, where, for example, as the picture shows here, the monomers sort of go AB, 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 alternating between one to the other. That's the type that we're going to look at in detail in the rest of this. It is possible. There are examples out there of random copolymers where they can mix in any order that they like. Block copolymers, where you get a series of one monomer and then a series of another monomer, and even something called graft copolymers. But we are not so interested in those right now. We're going to look at some examples of alternating copolymers. So here is a really good example. Terylene. It consists of 2 monomers. One of them is a diol. Remember, that's an alcohol with basically 2 alcohol groups in the same molecule. And the particular one that I want to show you here is ethane 1,2-diol. You can see there's the 2 hydroxyl groups at either end. This, to me and you, is antifreeze. So this is a chemical that you have seen before. We put it in engines. We put it even in windscreen wiper fluid so that we do not freeze our windows in winter. Now, the other monomer is dicarboxylic acid. In this case, terephthalic acid. Now, this is a derivative of turpentine, which is itself a product of like pine trees. It's got this benzene ring in the middle, so it's benzene 1, and then it's 4 carboxylic acid. So it has the 2 carboxylic acid groups on either side. And we obviously, terephthalic acid means it's a derivative of terps. So what happens when we get this terps derivative and this antifreeze and we put them together? Then what we find is the hydrogen of the OH group of the antifreeze basically will run away with the OH on the carboxylic acid group of the terps derivative. And so water gets liberated and is released. And what is produced is an ester link. You can see an oxygen forms in the mid-chain, what is left over from the alcohol group on the antifreeze. Now this produces a polymer, and this particular polymer, you will have seen it before. It makes that really iconic black synthetic material that's used in the straps of backpacks, the ones that feed through the little things and then click together. And now that is used in backpacks across the world. It's a major material, to the point where the total industry for this one polymer is about $60 to $90 billion per year. Globally, it's huge business. Now, in that previous example, the small molecule that was released was water. And we did say that it didn't have to be, that condensation polymerization can release some other small molecules. Here is an example. We've got an acid chloride. So in this acid chloride, it's an acyl chloride or diacyl chloride in this case, we've got 2 chlorines on the end of this molecule, and we've got the 2 double bond oxygens as well. Now this, its proper name is oxalyl chloride, and this is going to be the monomer that can bond with ethane 1,2-diol. So again, we've got antifreeze this time, but this other thing, oxalyl chloride. Now what's going to happen is here is the hydrogen of the antifreeze is now going to bond with the chlorine, or one of the chlorines in the oxalyl chloride. What gets liberated is hydrogen chloride, HCl. And what we get is a new material. The polymer of this is called polyethylene oxalate. And so you can see it doesn't have to be water that gets produced, it can be other things as well, but that depends on the monomer. So check out these 2 monomers. This is a much more complicated example with 2 aromatics. Terephthalloyl chloride and also this p-phenylene diamine. Right, so what are these 2 things? Okay, first of all, the first one, it has chlorines and it has oxygens and it has the benzene ring in the middle. The other one has got a pair of amino groups attached to the benzene ring. Now what can happen is the hydrogen, one of those amino groups, can go and form a new small molecule, HCl, that gets liberated, and then we get a carbon-nitrogen bond that forms. And so this produces a substance, and what you can see on this diagram on the right hand side of the bottom, sort of just behind my head, is it forms a very strong structure, and a strong structure where one polymer can actually form hydrogen bonds to another line of polymer, making it extremely tough. And though it's very flexible, it can be made very thin, it's almost unbreakable. This is Kevlar. Now the company DuPont is the main company that makes this. It's used in all kinds of bulletproof vests, stab vests, any kind of protective equipment for military use, worth about $2 to $4 billion every single year. Now we did speak about this when we were looking at the amino acid chapter, but remember that the amino acids contain both an amine group and a carboxylic acid group, and they can form a polyamide that has a repeating monomer. And so you can see here we have the straightforward, very simple amino acid, and you can see that water will get liberated and it will join together, and we're going to form what's called an amide linkage. Now, a polyamide with many different amino acids gets a different name. We call it a polypeptide. In this particular example, they're all the same, so it's a polyamide. A very long polypeptide folded into a 3D shape is called a protein, and believe it or not, both you and I are made of those. We can make polyamides from 2 different monomers, and this is going to get more and more complicated, but to understand that the basic principles are all the same. So the two monomers involved in this particular example I want to show you, first of all, you need to have one that contains two carboxylic acid groups, or a dicarboxylic acid as it's called. In this particular one, we're using hexanedioic acid. Hexanedioic acid, that's the pronunciation. It's hex because it has 6 carbons in the chain, and it's got the carboxylic acid group on either end. Now the other monomer needs to have 2 amine groups, the 2 NH2 groups. So diamine is the name of this kind of chemical, and this particular one is 1,6-diaminohexane because there are 6 carbons in the line. Now let's see what happens when we join these together. The mechanism is really simple. We're going to have the hydrogen in the amine group bond with the OH group that is of the carboxylic acid part of the dicarboxylic acid. So we're going to get water that is produced and liberated, and the two are going to join together. The actual particular monomer, or the repeating pattern of the polymer, we should call it, is quite complicated. You can see it there drawn in skeletal formula. But this is really significant to us because these two chemicals are used to make nylon. And nylon is a wonder material used in the production of clothing, waterproof clothing, especially puffer jackets and the like, $20 to $30 billion industry every single year. Now, we don't necessarily have to create nylon via the liberation of water. We can choose our chemicals to create the same thing, but via the liberation of hydrogen chloride if we choose a diacyl chloride instead. As it happens, both of these ways of doing it aren't the way that we do it in industry. We actually we use a monomer that starts its life as a chemical called caprolactam, which is a cyclic amide, and it gets heated so it opens up, and that forms the monomer that then can join together with other things. So basically there are many different ways of making the same polymer here, but ultimately one of the polymers that it creates, nylon, is one of the most useful polymers that we have ever discovered. Now, an important thing when we are attaching amines to carboxylic acids is what we get, the bond in between, the bond that forms at the liberation of the water. In this case is a double bond oxygen going to a nitrogen bond and that connecting to the rest of your chemical. And so that is the amide bond. We call that thing, the link between the two monomers, the amide bond. Now, so why is this all so important to us? Is because the industry that surrounds polymers is one of the most lucrative areas of all of chemistry. The global market for polymers that are synthetic and used in plastics and fabrics and composites is between $790 to $800 billion in a single year. So one of the largest industries on the planet. So condensation polymerization occurs when we join these monomers together and we snip off the end atoms and create water molecules or something similar. So we get water given off from the process. But what we could do is, and it was a case when we looked at those disposable stitches, that they could come under attack, the polymer could come under attack when exposed to water once more. Now, it's not necessarily the water in this case, but it's the H+ ions and the OH- ions when water dissociates that could attack these polymers. And this process of coming under attack by these ions is called hydrolyzing. If we go back in and we break the bonds connecting the monomers and the polymer, and we finish off those molecules with OHs and H+, then we can get the monomers back again. Why would we want to do this? Because it means that what we can do is reform those plastics again. If we can break the plastics down back into their monomers, then we can chemically salvage the monomers that they're made of and form them back into new plastics. And we have several different plastics that we can really effectively and economically do these to. These are what we would know as the recyclable plastics, the ones that we would put in our recycle bin, in the hope that one day they could have another go. Not for single use, but for multiple use. They get turned back into their monomers and then reformed into polymers for them to go on and live life a second time round as a brand new carton of milk. Here's another example that I want to show you, polytrimethylene terephthalate. It is a type of polyester, and you can see that the repeating pattern structure of this is quite complicated. So if you look at basic PET, that's a recyclable plastic, that's the repeating pattern at the top. You can see that it's just got two sets of a CH2 group between those two oxygens. But PTT is different, and it has three sets of carbons between the three. Now that changes the entire structure of this plastic. It's no longer a hard plastic you use for a water bottle. It actually makes it more flexible and therefore useful in textiles. In fact, this, what is called PTT, is the polyester that is used to make carpets. So can we put this under hydrolysis and break it down into its individual monomers? Can we recycle this material? Yes, indeed we can. There's actually two ways in which we can do it. There's one way that involves exposing it to a base, or sodium hydroxide, and a second way that involves exposing it to acid. So let's talk about the base first. Now, a very important thing about this is a base hydrolysis of this polyester is breaking the ester link. And whenever we do that, we actually have a word for that, and that was saponification. And look back at the ester topic so you fully get a grip of what that is about. But if we expose this polyester to sodium hydroxide in solution, then what happens is the ester link is broken, the Na plus ion goes and attaches directly to the oxygen, and the OH minus, the hydroxide ion, goes and attaches to the other half. And so we end up with two products, sodium terephthalate and 1,3-propanediol, which basically means, yes, we can, in exposure to a base, we can send this polymer back to its monomer structure for recycling. But hey, look, we can also do it with acid. Exposing it to H+ ions in solution will have a very similar effect. We can no longer call it saponification, but take a look at this. What we've got here is the H+'s have now bonded with the oxygen and broken the bond between the oxygen and the carbon. And what we will also find is the H+'s have also gone and bonded on the ends of the other monomer as well. So we form two products this time. Terephthalic acid. Why? Because we can see we've got a carboxylic acid group on both ends now, and 1,3-propanediol. How about this? This really looks quite complicated now. I can see two benzene rings in there. I can see all sorts of things going on. Well, this is the repeating unit of a fabric called Nomex. Now, Nomex is a high-performance aromatic polyamide, best known for its heat resistance. It is the material used in firefighters' protective clothing, and it's also used in all sorts of things. Also made by DuPont, and so a huge industry. Now, the backbone of Nomex contains these two benzene rings, which makes it very stable due to resonance. They don't easily break apart when heated. It gives them high thermal stability, exactly what you would want if you were a firefighter wearing this material. So what we can do with this substance is we can, of course, hydrolyze it. And there's two different ways. We can do a base hydrolysis and we can do an acid hydrolysis. Now, not a saponification, because we are not breaking an ester bond, we're breaking an amide bond. So you can see in between where the nitrogen and the carbon are bonded in the middle of this repeating unit, we're going to go after that. What is going to happen is that hydrogen is going to bond to the nitrogen, and that the sodium is going to go on and bond with the carbon. And so it's going to break there, and we end up with two chemicals that are almost impossible to pronounce, phenylene diamine and isophthaloyl moiety. What a strange name. But there we go. We can break this into two quite different monomers. And finally, we can have this undergo an acid hydrolysis too. In this case, the monomer on the left gains an additional hydrogen, additional H+, and so we end up with a structure kind of like ammonium. The ammonium ion is starting to appear at either end of this monomer, and it becomes the almost unpronounceable phenylene diammonium ion. Yeah, that needs a bit of practice. An isophthalic acid, which is, of course, a carboxylic acid, as you can see just there. So what we can do, and the main point of this is we can put together various different polymers from monomers, and we can also send them back again. Now this sending them back again is how we make these plastics recyclable. The entire plastics industry is one of the most important applications of chemistry.